Hey everybody, here's the second part of the Unit 7 review packet. So let's make sure you know what we're talking about. Unit 7 review, and then this is the second part of it. Alright, so when we graph an exponential equation, this E is a constant, so that serves as our base. Remember that E is about 2.7. We don't need to know that. It doesn't matter. When you enter it into the calculator, you get a couple points that you can basically guesstimate where they are by using estimates. But because E is not a rational number, the only one that's going to come out is when you have E to the 0 power. And because it's my exponent is plus 1, that means that this entire graph is shifted to the left 1. So e to the, when x is equal to -1, that's where I get my output of 1. Everything else I have here is an estimate. There's no vertical shift, so my x-axis is my asymptote. Anything can go in, but I am limited to what comes out by that asymptote. All right, so for number 10, we have some quickies about whether or not it's growth or decay. And what you're looking at in each of these is going to be your base and where the graph is going. So for letter A, I see that this base is greater than 1, so it's growth. Now this is negative, which means it's going to look something like this, but it doesn't matter, it's still growth. It's going away from the axis. This is my base. Even though it's a fraction greater than 1, so that's also growth. Here's an example of a base that has a fraction that's between 0 and 1, so that's going to be decay. And even though it has this coefficient stretch, that doesn't matter. This is the base, the fraction, so I'm taking the fraction of a fraction of a fraction, so it's getting smaller. Think about if I gave you a piece of a piece of a piece of a piece of a cookie. You'd be getting a smaller amount each time. Decay moves towards the axis, growth moves away. All right, so when we look at these short answer, we're just looking at transformations. My asymptote is determined by my vertical shift. So that horizontal line at x is equal to 15 is going to be where this graph approaches, snuggles up, never quite reaches. Anything can go into an exponential function. So even though it's negative, even though it moves to the left 16 and down 11, nobody cares. For an exponential function, your domain is all real numbers. When we look at number 13, we have the end behavior of this graph. Because it's an exponential growth that's negative, it's going to be growing away from this axis. And so as x approaches negative infinity, it's going to reach the asymptote. And this asymptote here is going to be at y is equal to 8. So our y values are going to approach. Now it's approaching it from the negative, but they don't care where it's approaching from. I'm just getting closer and closer to 8. All right. So real quick, down and dirty, what are these transformations? So they give me the parent function each time. So here's a parent function. What changes? It's reflected, it's stretched, and it goes up 5. From my natural log, it's going to be stretched, and it's going to move to the right 4 because of this naturally negative scenario. That graph is going to go that way 4. When we look here, we have a exponential decay as my parent function. It's going to be stretched. It's going to go to the left 1, and it's going to go up 3. Here's an exponential function with 2 as the base. It's going to be compressed. I'm going to have a third of the height that I normally would get, and it's going to go down 8. Okay, so for this next part, I'm covering up my answers so you can't see them. But what I want you to do is just pick the ones you know first. Example, you should be able to look at this and identify that as a quadratic easy. You should be able to identify this as a linear. If I see the x up in the exponent, you know that's an exponential. Because this x is down in the denominator, that's when we end up with that rational conversation. When you look at what's left, your quartic and your cubic are easy to find. So then you can go ahead and see if we match with our letters as we identify what type of family each of these equations belong to. Okay, so we can talk about each of these problems one at a time as we go. The price of a new home, that's going to be my initial amount. It appreciates at 2%. Appreciates means that it grows. So it's going to be 1 plus that 2%. And when I go ahead, they went ahead and gave me this equation. So I don't need to worry about writing the equation, although I could. They wanted to know if t was 10 years, what would this be worth? I put my value in for t using function notation. There's no math happening here. I'm just keeping track of it. Here's my 10 up there. And this is an easy calculator problem for me to add. So in 10 years, my $350,000 house is now appreciated to $426,000. That's pretty awesome. All right. So this one I haven't worked on yet, so we'll do this one together. I have 200,000 endangered birds, and they're decreasing. So I know that this is going to be a 1 minus problem because they're decreasing at 3.7%. The exponential function, here's my initial amount of birds. And if I put into the calculator, 1 minus this 3.7%, 0.037, and you can see how I write that in. This 0.963 is where this number comes from. Okay, what am I looking at? 100 years, what's going to happen to our birds? Are you ready? So the population in 100 years is going to be equal to how many I started off with times my rate of decrease to the power of how many years I'm talking about. And this becomes a simple calculator problem. Okay, so I have this entered into the calculator. Here's my 200,000 birds. Here is my exponential rate of decay, because I know that this rate value is less than 1, and that's going to happen for 100 years. And after 100 years, I'm only left with 4,609.55 birds. That's a pretty sad story. All right. So when we talk about a value being continuously compounded, we're looking at that rate happening over and over and over and over again, and that's where E enters into the conversation. So my initial amount is $5,000, and that E represents that constant value. Remember, E is about 2.7. It's an irrational number, and the calculator inserts that value for you. And we talked about how mathematicians discovered it. If you can't remember that story, that's okay. All that you need to remember is that it's a constant in mathematics that we can use when we're continuously compounding interest and a value. Remember, your interest is given as a percent, so you need to make sure that you enter that correctly as that decimal value. So 5,000, how much money you put in, times E, there's my rate, there's how long, and at the end of that 30 years, that $5,000 becomes over $39,000. That's a pretty good return on that investment for sure. Okay, now we are getting $1,000 for our birthday. How much would I have in 60 years? and I have 7.2%, and I'm going to make sure that I write that decimal, including that percent, so I don't mess up with that, and I remember that 0. Okay, so the amount that I end up with after I put my $1,000 in, it's going to be multiplied by E, and that E is going to be raised to my rate of growth, and then for however many years, and I believe 60 years. I don't know, you're going to have to forget about that $1,000. So my $1,000 is going to be times, we're going to go ahead and do my E to the, and I want to make sure that I have a parenthesis so that the decimal multiplication problem, everything is inside the exponent position. So that $1,000 is going to turn into $7,518 at 7% after 60 years. Didn't sound like as much growth as we were hoping for. Hey, wait, did you see where my mistake is? I did $100. We need to make sure we do 1,000. That sounds better. So we're going to go times E to the 0.072 times 60. Now we'll make sure we have that right. Close my parentheses. There we go. That sounds better. 75,188. It didn't seem like enough money to me, so I went back and double checked, and sure enough found my mistake. So make sure that you think about your answers while you're doing this. All right. So let's take a look at these last two. They say switch from exponential to logarithmic form. So when I go ahead and I'm using my logs, I know that my base goes down on the bottom of my log, and that outcome of that base and that exponent is what comes next, and then that exponent is what we have here. Remember, we're always solving for the exponent. So this exponent is going to be in the output position of our equation. I actually did a little research because I was looking for the right term for this, and if you can Google it and figure it out, let me know, that'd be great. But from what I got, nobody had a real answer for what that value is called. All right, so because I have a base of a 10, I can use the common log without writing any kind of base here. When I have that outcome of 100,000, I want to make sure you can tell the difference between my word log and then my exponent of 5 is what made that happen. All right, now we're going to think backwards. We're given the log, and we need to rewrite it as an exponent. So I go ahead and I start with my base, and I know that that's raised to the third power, and then that is that value that is in the output position of the exponential output. Maybe we'll start calling it the exponential output. Of course, when I see the ln, I know that that has e as a base, and my exponent is 0, and anything to the 0 power is 1. All right, so we're going to keep moving on and look at this last one page that we have for logs and inverses. When they ask you to find the inverse is actually a new equation. It's a new function that we are creating by swapping our x's and our y's. So if I have this equation here, y is equal to the log of 1/3 to the x, my inverse happens when I swap my x and my y. Now that I have this new equation, if it's given to me as a log, I can rewrite it as an exponent. So that means that 1/3, there's my base, to the x power is going to be equal to y. And what we're going to do is we're going to put a little -1 up top, and that reminds us that that is the inverse 1/3 to the x is equal to y. Okay, let's come over and do this one. If I'm given y is equal to 4 to the x, my inverse happens when I swap my x and my y. Now, in order to solve for this y, I need to try to get it out of that exponential position, and my log is going to help me do that. So the log of the base 4, remember the log is the exponent. The log of this base with this outcome is equal to that value. And again, we'll go ahead and we can put that -1 on it to make sure that we all understand that that's going to be an exponential equation. All right, let's keep going. If I have y is equal to the log of base 7 with the value of x, my inverse is x is equal to log 7y. And I'm going to go ahead and rewrite that in an exponential form. So I'll have 7 to the x is equal to y. And I'll remember my -1 to let everybody know that that's the inverse. My original function, y is equal to 1/2 to the x power. My inverse, swap my x and my y. Now notice, if I have a log, I solve it through exponents. If I have an exponent, yep, I'm going to solve it through finding the log. Remember, I'm looking for that as an output. So the log of the base 1/2 that results in x is equal to y. All right, so those are the inverses. All right, here's this next part, and I did the first couple of these evaluating, and whether I talk about with an x here, I can do that to make it easier for me to go ahead and solve for x. I don't need that x. I can just say the value of this is 3, and the value of this is 2. The value of this is -3. Sometimes it makes it easier for kids if they have it actually equal to something, then they feel like it's an equation that they're solving for to find that value for x. So if I make an x here, 4 to the 3rd is going to be worth 64. No need for logs there. 2/3 to the 4th power, if I say that's equal to x, 2 to the 4th power is 16, and 3 to the 4th power is 81. So that fraction has that value. If I say that this is equal to x, that means I'm dividing by 5 4 times is equal to x. And I believe this is 625. But if I'm worried that that's not a part of my friendly numbers, I'll go ahead and ask for my calculator, what is 5 to the 4th? And yep, I was right. All right, so now we'll just talk about here. If we want to put that x on here, I want to say 5 to what power is equal to -7. And guess what? That's one of those undefined ones, because I can't have this value being negative, because I want you to think about something for our exponential graphs. Remember, they go like this, and we have this area down here that we don't have a negative outcome. A negative exponent gives us a fraction. So without any kind of transformation, my graph is not going to have a negative outcome, which means that's not a possible. That's why it's undefined. All right, let's talk about this one. If I put an x here, like something I'm solving for, then I can say 9 to what power is equal to 5/16. So guess what? We're out of our friendly numbers. We don't know. So this is where, this is one that we're going to have to go ahead and use either Desmos or the TI graphing calculator. So so let's see which calculator I grabbed today, whether I have my old one or my new one. And I have my old one, which means I have to do the change of base formula. So I'm going to do the log base 10. And remember, we're back to this formula. The log base 10 of 5/16 over the log base 10 of 9. My change of base formula, this base, remember, goes to the bottom. So when I type this into the calculator, it's going to look like this. I want the log of 5 divided by 16, and that's going to be divided by the log of 9. So my x value there is, my x is equal to negative 0.5. We'll go ahead and round that to 3. So guess what that means? 9 to this power is that. And you can check your answers. Go ahead and do it. 9 to the negative 0.53 power. You get a decimal. Go to math, frac. And then, oh, it's not going to give me a... So let's go ahead and see what 5/16 is worth. See, pretty close. So I know that this was more of a rounded value. That's why the calculator couldn't put it in. But look how close my answers were. So that means that I did it correctly. All right, so log base 8, that gives you 0.32. Let's go ahead and go to the calculator. And we'll go ahead and put that through my change of base formula, where I'll say log base 10 of 0.32 over the log base 10 of 8. So we'll have the, log base 10 of 0.32 divided by the log base 10 of 8. And that's going to, again, give us a x is equal to negative 0.5. We'll go ahead and round that. But then, of course, be ready to not exactly get the same answer, because what this is asking here is if we have x, that's 8 to what power is equal to 0.32. If I said 8 to the negative 0.55 power, then you can see that is pretty close to 0.32. So I know I'm doing it right if I check it with the calculator. All right. We have, if we call this is equal to x, we say 8 to what power is equal to 2. That's not anything that we can figure out. That's not part of our friendly numbers. So we'll bring the calculator back into play. And we'll say the log base 10 of 2 divided by the log base 10 of 8. And that's going to give us x is equal to 0.33. And again, feel free to always check your answers. Is that about 2? Yeah, that's pretty close. So we know we're doing that right. All right, so if we make this x, 6 to what power is equal to 0? So we'll go back to this conversation. An exponential graph has 0 as an asymptote. It approaches it, but never reaches it. So guess what? That's another one of our undefined ones. All right, let's think about this. Is equal to x. So 5 to what power is equal to 1? You got it. That one is a part of our friendly numbers. Now let's say it wasn't a part of your friendly numbers. You can still use those calculator strategies to help you solve it for sure. All right, so the next couple ones are, a lot of times we call them identities. They're ones that in mathematics you need to be able to look at and know automatically. So if I have the natural log of e, then I want you to think about what that means. That means the natural log base e that gives me e is equal to x. Okay, e to the x is equal to e. Of course, x is going to be equal to 1. So the natural log of e is always going to be 1. A lot of times in mathematics, you'll do this enough that you can skip this step and move right to here. Okay, let's think about this one. Okay, I've got the log of base 10 that gives me 10. Well, hopefully, by looking at this one, you can see if I put it into exponential, this base to this exponent gives you what? Yeah, guess what? That's going to be, and again, the more of these you do, the more you'll recognize that the log of 10 is going to be 1. Let's talk about this. The natural log of 1. We can always write it out. So ln means that we have a base of e. I got 1 as an output. So that means that e to what power is equal to 1? Guess what? Anything to the 0 power is 1. The more of these you do, the better you get. So keep thinking and working. Here's your best surprise. Nothing on the back. So guess what? You're done. I hope you're ready for your test on Monday. Thanks for tuning in. Bye.